Stripping down science. The Naked Scientists.
Hello, it's the 17th of October 2010. I'm Ben Valsler and this is The Naked Scientists. Today we'll be looking into the science of turbulence. We'll find out what turbulence actually is, why it needs some of the most powerful computers in the world to study it, and how we can stop it from happening inside pipes. Joining me today is Dave Ansell.
Also coming up is Mira and I find out how airflow through buildings can be controlled to keep the temperature just right, cutting down on the need for power-hungry air conditioning systems. In the news, we'll hear about a potential new vaccine for TB, the Rolls-Royce Science Prize and the comet that never was.
That's all to come on today's Naked Scientists, and if you've got any science questions, we would love to hear from you.
Tweet at Naked Scientists right on the wall of our Facebook page, or our email address is chris@thenakedscientists.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
This is The Naked Scientists, and as usual we shall kick off with a roundup of this week's science news. A new vaccine against tuberculosis could not only boost the effectiveness of the existing childhood BCG vaccine, but it could also offer protection against multi-drug resistant forms of the disease. TB is a global problem, with the World Health Organization estimating that almost 1 billion people will be infected by 2020. Multi-drug resistant strains of the bacteria are also becoming an increasing problem. The standard vaccine, the Bacillus calmette-guerin, or BCG vaccine that most of us will have had when we were a child, is very good at protecting against severe disease in children, but actually offers relatively little protection for adults. Attempts to boost the immunity by re-administrating the BCG have not been successful, so any new vaccine would have to boost this immunity as well as offer protection against drug-resistant strains. This new vaccine, which has been tested and found to be effective in a range of animals, consists of 4 proteins joined together along with a chemical known as an adjuvant, which actually helps to create the immune response itself. Each of these proteins has been shown to give partial protection against TB on their own, but because there are so many different strains of TB out there, no single protein is enough for a vaccine. By combining proteins into one supermolecule, the vaccine offers protection against a range of different strains of Mycobacterium tuberculosis, that's the bacterium responsible for TB, including a strain that's known to be resistant to multiple drugs. In guinea pigs that have previously been immunised with a short-term BCG, the new vaccine not only offered its own protection, but it also stimulated the release of immune components that were originally activated by the BCG. Now, this makes it a very good candidate for boosting immunity from the BCG, which has been given to millions of people worldwide since its first use in humans back in 1921. Chris.
Well, up into space now, and a tremendous piece of forensic work that means that scientists can pinpoint to, within a week or so, when 2 asteroids collided. Now, the story goes back to January of this year, 2010, when a system called LINEAR, which stands for the Lincoln Near-Earth Asteroid Research Study, which is a robotic scan of the sky, spotted this bizarre object up in the asteroid belt. Now, to all intents and purposes, it looked and behaved just like a comet. So it had a big long tail, about 200,000 kilometres long, and it was moving in the orbit of the asteroid belt. Now, that was a bit strange, because most comets come from deep space and they don't tend to orbit in the inner solar system like that. But it did have this big tail. One other slight strange thing, though, was that it didn't have any centre or nucleus, which most comets do have. So, on the one hand, it did fit with being a comet. On the other hand, it didn't. And so scientists have since been studying this in some detail to try and work out exactly what it is. Now we know. There are 2 lovely papers in the journal Nature this week. One of them is by Colin Snodgrass, who's at the Max Planck Institute for Solar System Research in Germany, and the other is a guy called David Jewett, who's at UCLA. And the 2 of them have used 2 different approaches to study this object. David Jewett and his group turned the Hubble Space Telescope to look at it, and what they saw was an object about 120 metres across with this tail extending behind it. What the other group Colin Snodgrass and his colleagues saw was actually done using the Rosetta mission, which is, ironically, a probe which was launched from Earth in 2004 to go and look at another comet. And because it's now out beyond the orbit of Mars, it could look back at this particular comet, or whatever it was, from a very different angle than Hubble, meaning that you were looking at it from two different directions, which would enable researchers to confine the parameters of what they were seeing much more closely. What that analysis revealed was that this was not a comet at all. What it was the proceeds of a big cosmic collision. What had actually happened is that one large asteroid, probably about 120 metres across, had gone barrelling into a much smaller object, probably about 3 to 5 metres across. The two had struck, and the debris that was liberated during that impact was then streaming out behind the asteroid, producing the tail that fooled people into thinking it was some kind of comet. What's really intriguing, though, is that researchers have been able to use how much the debris has spread out in that tail to work out when this collision occurred. The 10th of February 2009, give or take a week. And the way they know that is that the particles of dust can be seen to be moving because of photon pressure. So when light from the sun hits those particles, it causes them to spread out and move a certain amount. And obviously the small ones move a bit further than the big ones. But you can work out, therefore, how much light must be impacting on them and for how long to be moving the particles relative to each other. And that tells you when they must have been liberated from their parent body. And that's how the researchers have been able to wind back the clock to February of last year. Now, this is, in itself, a wonderful example of cosmic forensics. On the one hand, it tells us and pays homage to quite how good the observations and instruments we've now got to make measurements that are incredibly precise, even millions of miles from Earth. But the other is that it does inform our understanding of worlds and solar systems other than our own, because many distant stars and systems are surrounded by disks of gas and dust. And understanding where that dust comes from will help to constrain our understanding of the formation of those different distant systems, and therefore understand a little bit more about what might be in them. So it is a very exciting discovery because it advances our knowledge not just of this solar system, but of other systems many, many light years away.
Thanks, Chris. Now moving back down to Earth, a cheaper alternative to gold-plated connectors has been developed. More and more of our lives is becoming dependent on electronics, and that electronics is dependent on wires and cables. A cable needs a plug, and producing a good contact on a plug is actually quite challenging. The problem is that you want to make a connector out of a metal which is strong, conductive, and of course cheap. However, all the metals that fulfil these constraints, like copper, brass, etc., will oxidise in air. This wouldn't be a problem itself, but the oxides are insulating, so you cover your nice conducting contact with an insulating layer. The standard solution to this problem is to cover the contact with a very thin layer of a noble metal, which doesn't oxidise, something like gold or platinum. The problem is, of course, that gold is very rare, and so it's expensive. And because of historical reasons, it's used as a secure investment when the financial markets are feeling insecure. So at the moment, it's even more expensive than usual.
Exactly what we're experiencing at the moment, yeah.
Indeed. So there's getting to be a problem. Now, whilst it's not possible to stop these cheap base metals corroding and oxidising, Mark Aindow and colleagues at the University of Connecticut have been approaching the problem from the opposite direction. They've been trying to make the oxide much more conductive, so it doesn't matter that it's there. They've been using a variety of approaches to do this. One is alloying the original metal with one that has a conductive oxide, so that some of these scales of conductive oxide on the surface are conducting, so when they touch to something else, they'll conduct well. And another one is adding metals to the alloy, which effectively dope the original oxide, adding or removing electrons and allowing current to flow, a bit like you do in a semiconductor. The results are actually quite promising. They've increased the conductivity of copper contacts by about a factor of 3 by adding lanthanum, iron by a factor over 200 by adding vanadium, and adding ruthenium to nickel improves it by a factor of about 300. So the contact resistance only gets 20 or 30 times worse after 1,000 hours in an oxidising atmosphere, which, considering that it's not that big, isn't a major issue. Whereas if you hadn't added this ruthenium, it would get over 10,000 times worse. They're very encouraged by this result, as they're only using a few two-metal alloys and expect further improvements with more work and mixing 3 or more metals together. And this approach has the other advantage that there's no problem with the surface coating rubbing off, so in the future cables might not have to be gold-plated. I'm not sure it will stop the hi-fi manufacturers covering things with gold or platinum just to put up the price.
You can never quite tell if it's actually making a difference as well, but I'm sure there's something psychological. There must be a placebo element where you spend £50 on audio cables. It's got to sound better to you, even if it doesn't sound better to anyone else.
Placebo, I think, is what most of it is.
Thank you very much, Dave. Observations with the very obviously named Very Large Telescope have shed light on how early galaxies grew by funneling cold primordial gas into their core. Giovanni Cresci from the Archetri Astrophysical Observatory in Florence in Italy, along with colleagues across Europe, used SYNFONY, that's the spectrograph for integral field observations in near infrared, to observe 3 distant galaxies that formed only 2 billion years after the Big Bang. Using near-infrared spectroscopy, they were able to map the distribution of elements throughout these galaxies. Galaxies are thought to grow through a process of collision and merging, smaller galaxies colliding and becoming one larger galaxy. However, this doesn't account for all galactic growth. In fact, the 3 galaxies observed in this study showed very regular rotation patterns, as you would only expect to see in galaxies with very little or even no history of collision. These observations were looking for gradients in metallicity, that's the abundance of elements heavier than hydrogen or helium. Modern galaxies tend to have high metallicity in their central regions, with fewer heavy elements towards the edges. However, these galaxies showed the opposite gradient, lower metallicity in the central star-forming regions, and getting higher towards the edges. Writing in Nature, the authors argue that this points to the cold flow model of galaxy growth, in which cold primordial gas, fresh from the Big Bang lacking heavy elements, is funnelled into the centre of the galaxy, and that's what fuels star formation and galaxy growth. Now, this week, the winner of the Rolls-Royce Annual Science Prize was announced during a special ceremony held at the Science Museum in London. Chris Smith was there to hear who won.
In 2010, Japan filed 330,000 patents, America 240,000, Britain 17,000. Other countries are now dwarfing our technology output, use far more engineers than we do.
The numbers make quite sobering listening, don't they? But the main point that cyclonic vacuum cleaner inventor Sir James Dyson was making during his keynote speech at this year's Rolls-Royce Science Prize award ceremony is that if we're to keep British engineering open for business and internationally competitive, then we desperately need to invest in the education and nurturing of the scientists and engineers of tomorrow. It's a view that's shared by many leading industrialists and specialist manufacturers, including Rolls-Royce themselves, as the group's Director of Research and Development, Professor Rick Parker, explains.
We're very worried about the quality of science teaching and the sheer enthusiasm for science amongst young people today. They weren't going into science courses. They were often being put off science at a very young age, so there was no chance of them going on to university to do science or engineering because they just hadn't done the right subjects in the run-up to leaving school.
Rick Parker. To tackle this problem, the company have set up a prize targeting teachers. Vaughan Lewis.
Science Prize is an annual competition we've been running for teachers for the past 6 years. It was launched on our anniversary year, and the idea is we ask teachers how they would improve science education in their school or college with £6,000 from Rolls-Royce. We work through the Science Learning Centre network to get those entries, and each year we get between 1,500 to 2,000 schools that put an entry in, and from those the 50 best are selected to win £1,000 as a shortlist, and from that shortlist we choose 9 finalist schools, and those schools receive a further £5,000 to go ahead with their project ideas over the following academic year.
Why did you think there was a need to do this?
At Rolls-Royce, we are very committed to ensuring that the next generation of students coming through will have the right skills, the right understanding, the right knowledge to be able to work in companies such as Rolls-Royce, high-tech and high-value-added companies. So they've got the understanding of the basic science behind the things they need, and they're enthusiastic about it and want to go on and study at a degree level and beyond, so they can come and work for us, or want to come and work with us at apprenticeships and get their hands on and real science and engineering.
It's telling, though, isn't it, if a company like Rolls-Royce has to start putting together prizes to try and stimulate what many people would argue ought to be going on in schools anyway. That's what schools are for, isn't it? To try and get people interested in sciences and development so that Britain carries on as a manufacturing nation.
What I'd say about that is, the teachers do a great job. There's a lot of very good teachers out there, encouraging a lot of students to do these. But what we were trying to do with this money is allow them to do something above and beyond what they normally do. So with the £6,000, if you're in a primary school, that's a lot of money. Our winners last year were a primary school and they received a further £15,000 from us. So they received £21,000 from us. And when we spoke to the science coordinator at that school, his budget for the whole school was £700 for the following year. So we're able, through what we're doing, is just to give them a big boost and allow them to do more than they would do, just to really raise the profile of science and engineering within school and make it fundamental to what the pupils are studying.
Vaughan Lewis. So that's the theory, but what about in practice? Well, here's this year's winner to tell us.
My name's Robert Aspden. I'm a science teacher working at Teesdale School. I run a club called the STEM Club that's for science, technology, engineering and maths. It's supposed to encourage students to want to take on those careers in future, because England and Great Britain are getting behind a little bit with that, and we're trying to make sure that doesn't happen and we stay the great nation for engineers that we are. So the Rolls-Royce Prize has allowed my club to push the limits of what the students could achieve.
What was the project you did that won you the prize?
I had the students designing and building and researching enrichment devices for a captive group of primates, some mandrills at Chester Zoo. There's a big issue at the moment about zoos and the lifestyle that animals have. So we were setting about trying to encourage and develop the lives of these animals to stop them from going insane in the captive situation. So we work with Chester Zoo, who do lots of work with their animals, trying to encourage them to work for their food and prevent these insanity behaviours that can develop.
So what did the students actually have to do, and what do you think they learned from doing this?
The first part of the project, we visited the zoo, so they got to see the animals, and we had them studying the behaviours of the animals, so that then when they went on to design the feeders that we made, they actually made them linked to the animals. So after we did the research using, obviously, the internet and other resources, they had a design phase where they designed and built the feeders. We then gave those devices to Chester Zoo, and a former colleague of mine who works for Salford University is doing an extended longitudinal study on whether we have or haven't actually benefited the animals, because we wanted to prove scientifically that we have actually enriched their lives, rather than just say, we built these toys, we gave them to them, we've done our job. We wanted to actually prove that.
What about the children who took part in the study? How old were the students, and what do you think they got out of it?
Well, there's two parts to that answer, I suppose. The club is a Key Stage 3 club, so that's students of ages 11 up to about 14. The benefits to them was to do things like just encourage their thinking behaviour, their team working, their skills about technology and science, so they can see how all that actually links together in an applied sense.
And what about in terms of the long-term goal for Rolls-Royce? Because I've spoken with Rolls-Royce, they tell me that their aim is to try to get teachers like you to stimulate students to become the engineers of tomorrow. Are you seeing evidence that the students that you have got involved in this project are going to go into research to benefit Britain in future?
As part of the project, we actually did some analysis through questionnaires where we asked the students their opinion of STEM-related subjects, STEM careers, and whether they were interested in moving into those areas. Quite a lot of them said, as a result of this project, we'd either encourage them to take on STEM-related subjects at A-level, possibly university, and there was definitely a positive relationship in the number of students who then thought they would actually be interested in careers in that. And there were a number of students who actually said, because we'd done something unusual looking at primates and biology, they didn't realise just how much engineering could be related to that side of science as well. So they were quite interested in doing that too.
Science teacher at Teesdale School in Durham, Robert Aspden, who won this year's Rolls-Royce Science Prize. There are more details about the prize on the web at science.rolls-royce.com. So that's the school side of the equation. But what about higher level training that will turn university students into the specialist engineers and materials scientists of tomorrow? Well, in the last 12 months, Rolls-Royce have also launched a multi-million-pound initiative called the Strategic Partnership, which aims to do just that.
I'm Neil Glover. I'm a materials scientist at Rolls-Royce, and I'm responsible for the content and execution of the research programme within the company. The strategic partnership is a partnership between Rolls-Royce and the EPSRC, the Engineering and Physical Sciences Research Council, that enables us to fund research in our preferred universities within the UK on a whole range of material science topics that underpins all of our technology going into engines.
People might say, well, Rolls-Royce is a big company. Why doesn't it fund its own research? Why do you need to work with universities for that?
Well, the universities enable us to provide a level of deep independent research on the more academic aspects of material science that can then underpin the work that we do in company to deploy that technology into engines. So it's the freedom for the academics to think, to explore, to check out new technologies and to investigate problems and detailed issues of materials understanding that we just simply don't have time for in the day-to-day business.
So looking at the nuts and bolts of how the partnership works, is this just a research exercise, or is the aim here also to try to get people in a position where they could then go on to have progression in Rolls-Royce if they chose to do so?
It's absolutely that. Rolls-Royce is very much dependent upon the recruitment of highly skilled material scientists, and traditionally that has always come largely from our own internal supply chain through the universities and through the research base. And so the strategic partnership, as much as it develops technology, also develops people who we can recruit into company or who can go into academia.
Neil Glover talking to Chris Smith. And that strategic partnership also funds PhD studentships in materials science at some of the UK's top universities, including here at Cambridge. If you'd like to apply for one or to work on the materials that will drive the jet engines of the future, there are more details online at nakedscientists.com/Rolls-Royce.
Distilling the best science. The Naked Scientists.
You're listening to The Naked Scientists with Ben Valsler and with Dave Ansell. Coming up, we explore the world of turbulence and find out why turbulence in pipes could be keeping the cost of living up. Now, walk along any beach, almost anywhere in the world, and you'll find plastics washed up on the shore. From plastic bags to lighters, bottle tops to flip-flops even, plastics have even turned up on the coast of Antarctica. But it's not only the visual effect of this human detritus that's a problem. Plastics actually carry pollutants and even life around the globe, sometimes having serious consequences. Planet Earth podcast presenter Richard Hollingham joined David Barnes from the British Antarctic Survey on the Pebble Beach, in the wind and the rain sadly, at Cley in North Norfolk.
So we're going to walk along two strand lines, one the storm line, where the last time that there was a big storm has deposited lots of natural debris but also man-made things, and along the strand line from the last big tide. And we're going to walk along and look at some of the more persistent items of debris, particularly plastic, and see what it tells us about the ocean far away from these shores.
So we've got here is a plastic bag, and I think we can probably tell from the green lettering which supermarket that's from. It's torn and it's gone translucent, but it's still retained its essential plastic bagness.
Yeah, plastic bags are made of very, very thin plastic, so they break down relatively easy with salt spray and UV light as long as they stay in the top layer. But even this could have travelled quite some distance, and we can see that looking at it closely, you can see all sorts of things have started to get a grip on top of it, including foraminiferans. So life has started to colonise this plastic bag.
That's amazing. You've also got down here, we think this is probably the heel of a shoe.
What will happen with a lot of this material is when it starts to get broken up, the surface has got a very good texture for settlement because it slows down the water over it. Its boundary effect will be slightly stronger than the smooth pebbles and other smooth things that are typically floating. So life can get a grip and then it can be carried around. But it's not just life. These plastics will absorb all sorts of things such as toxic chemicals and transport those around as well. And so various groups over the UK and elsewhere have been studying what plastics can carry, how far they're carrying them, and what sort of effect they have.
And that, for you, is almost a bigger issue than, yes, they're not aesthetically pleasing to see on a beach. Here we've got a green bottle top, there's a little bit of string here, the plastic bag. But it's the fact that not only these spread toxic chemicals in the environment, they carry life around the environment.
Yeah, and we can see on this piece of plastic twine that we've actually got two different species of hydroids, one on the base there and another one halfway up, and they're actually reproductively active. They'll be releasing larvae, so this is not just transporting the adults around, these will be producing larvae that will settle wherever this goes.
So these tiny little, almost twig-like projections on the side, they're alive, and so they kind of mingle in, they almost become part of the twine there.
Yeah, and actually I found a third species. So we've got three species just on this insignificant little piece of twine. These species are probably native to the UK, but there'll be other species that come in that aren't. And that's where the problem is, that it can make a big difference to local aquaculture and fisheries if some alien pest gets in, becomes established, and then really starts to outcompete or eat our native fauna. And with these pieces of plastic travelling for many years, perhaps decades, that means we could get animals and algae and other organisms from all over the world landing on our shores.
It doesn't, I suppose, matter that there's this twine with these life clinging onto it here, but it might matter in other parts of the world.
It's still a problem here, but it is more a problem elsewhere. We have to remember that looking along this strand line here, we can see lots of natural material. We can see seaweeds and we can see bryozoans and other animals, especially crab shells, that have floated here naturally. And they've been doing this for a long period of time. For hundreds of millions of years, life has been floating around this part of the world. But in the polar regions, where there aren't lots of things that float, there aren't shells that naturally float, and there aren't seeds and logs and other material that we would naturally see on our strand line, then plastics there and other floating man-made debris has made a huge difference, because it's created this new environment of things floating on the surface, transporting organisms that wasn't there before.
That was David Barnes from the British Antarctic Survey talking to Richard Hollingham, the presenter of the Planet Earth podcast, on the beach at Cley in North Norfolk. And if you enjoyed that, there are more of Richard's podcasts, as well as links to other Planet Earth resources at thenakedscientists.com/Planet Earth.
Still to come, we'll find out how cleverly controlling air movements can cut down on the need for air conditioning, and Diana O'Carroll finds out why travelling backwards can make you feel ill.
If you've got any burning questions on this week's topic, that's turbulence, if you'd like to contact us through Twitter, it's at Naked Scientists, you can tweet that, or you can post a comment on our Facebook page, or send an email to chris@thenakedscientists.com. Now, today's topic is turbulence, and when most people hear the word turbulence, they immediately think of being thrown around inside an aeroplane and perhaps needing to use those little paper bags that they supply us with. But the way that it affects flight is just one aspect of a very large and very complicated subject, as I found out when I spoke to Dr. Fred Marquis from Imperial College London.
Turbulence itself is actually quite difficult to define as is. It's actually a mixture of things, and we usually try and classify it. Some people actually call it a syndrome. But turbulence is characterised, I think, by three main things: disorder, mixing and vorticity. By disorder, I mean that if we look at a flow that we call turbulent flow, if we look at a point in that flow and measure very carefully what's going on at that particular point in terms of either temperature or the velocity of the flow, if we look at the data that we get out from that point, we see that it's got very small, sometimes large, seemingly chaotic motions that seem to vary almost randomly as a function of time. But if we measure for long enough, what we can see is over that long period of time, a mean value appearing as we take our measurements. So the measurements, if we average them all out, seem to come to a mean or a steady value.
What do we mean when we say mixing and we're talking about turbulence?
Okay, probably an easy one for you to visualize is ink mixing into water. If you start off with a nice blob of blue ink, and you've obviously got the colourless water, the blue ink is very easy to see, and the blueness of the ink will propagate out into the rest of the fluid, and the colour of the fluid will become more and more even over time. And that takes a long time, because the essentially mixing that is taking place there is by molecular motion. If, however, we take a spoon and we stir up the ink and the water, you will see the colour will even out extremely quickly. And that is because as we stir the fluid, we're imparting turbulence into the fluid, which causes this very high rate of mixing.
So to make something turbulent, do we actually have to add energy?
Spot on. That's exactly what you have to do. And it's worse than that. To keep the turbulence going, you have to continually supply that energy, because over time, the natural viscosity of the fluid, which you can think of as fluid friction, tends to slow or absorb the turbulent motions and ultimately convert those into heat.
Okay, so that's turbulence and mixing. And the other one you mentioned was vorticity. Now, vortices are these, most people think of them as smoke rings, aren't they?
Yes, that's a good analogy to look at. A smoke ring is a very well-defined vortex. Again, if you look at a turbulent flow, and it could be off the front of a ship or it could be around a bridge support, you will see quite pronounced curly motions. I mean, even Leonardo da Vinci, in some of his sketchings, he was actually sketching these vortical motions within the fluid. And of course, with our eye, what we tend to see is the big motions. But in actual fact, what's happening is that these big vortices are getting stretched over time. As they get stretched over time, they get thinner. Because they're getting thinner, they're getting faster. And as these vortices get faster and faster and longer, they become unstable. They break up into smaller vortices. So you get a whole cascade of vortices, and we call it a cascade of energy.
So obviously turbulence is a very interesting thing, a very difficult thing to study, but why is it important that we do actually research it?
Turbulence is important. The two that I'm perhaps most familiar with are in things like the chemical and pharmaceutical industry, and also in the motor industry in the design of combustion engines and indeed gas turbines for aero engines. Now, one of the processes that's going on in combustion is obviously combustion. You're mixing fuel and an oxidant, usually air, together to produce heat, and you want that heat to be able to then ultimately do work and push your aeroplane forward or move your car along the motorway. But how that air and the fuel mix within the combustion chamber determines quite critically the efficiency of the combustion process going on within the combustion chamber. And the efficiency is measured in two ways, if you like. One way is how much of the fuel gets turned into useful heat. And the other thing that happens is during those chemical reactions, pollutants get formed. The amount of those that you produce is dependent upon the levels of turbulence and how efficient the mixing is within the combustion chamber.
You also mentioned the pharmaceutical and chemical industries. In what way do they need to understand turbulence?
In exactly the same way, in the chemical and pharmaceutical industry, you've got chemical reactions going on. And sometimes you've even got competing chemical reactions going on. So, for example, if I'm trying to make a drug and I mix two chemicals together, I may well get my drug, which is what I want, but I may also get some side products which I don't want. And the amount of side products can be critically dependent upon the levels of mixing that are going on in the pharmaceutical process. And by controlling the levels of turbulence, for example, by controlling how you actually do the mixing in what's called a mixing vessel, you can tune your process to produce the chemical or the drug that you want to produce and try and minimize the side products.
So clearly understanding turbulence is very important, but how do we actually go about researching it?
Okay, if we actually want to try and understand what's going on within turbulence or within a turbulent flow, I suppose you've really got sort of two avenues of approach. The first is an experimental method, so you actually set up your flow and you carry out measurements. And these measurements are usually laser-based, for example, and we like to use laser-based methods because they don't disturb the flow. Another way of trying to understand what is going on in turbulent flow is that we can actually try and model the turbulence. And when we model this turbulence, we have to resolve all of those chaotic motions that I was talking about earlier. And this means that there's a very high computational cost. In fact, one of the biggest computers in the world is modeling the weather. And these weather modeling computers, computer programs, essentially they have to be large because they're trying to resolve all the turbulent flow within the atmosphere.
And that is an awful lot of turbulence, especially judging by how accurately we can predict the weather nowadays. That was Fred Marquis from the Department of Mechanical Engineering at Imperial College London.
Turbulence occurs in fluids, and one way we often transport fluids around is in pipes. Now, Tobias Schneider is a researcher at Harvard University, and he studies turbulence in pipes. Hello, Tobias.
Hey, hi.
Is turbulence a big problem in pipes?
I guess it is. I mean, if you transport oil through pipelines or water through city water mains, then it just costs much, much more energy if the flow is turbulent. So you want to terminate turbulence in these kind of systems.
I guess turbulence is swirled, so it's happening in 3 dimensions. So is it difficult to study because it's hard to kind of separate everything out?
Sure. So what you have to do basically is you have to set up a simple experiment to do that, and that's basically what we did.
So what exactly were you doing?
So we were setting up an experiment where we had water flowing through a long glass pipe about 12 meters long and 3 centimeters in diameter or something like that. Then we created a patch of turbulence in this pipe, so a local region, which is also known as a turbulent puff, that moves downstream within an otherwise laminar flow.
So did you have to actually trigger the turbulence yourself, or would it develop naturally?
No, in this case, it didn't develop naturally. So if you have a very smooth pipe, then you have to perturb the flow. So we injected a little bit of water into the pipe that then generated this turbulent patch that travels down the pipe.
So it's one of these things where you start off with a little disturbance and the disturbance gets bigger and bigger and bigger, and in the end you get problems.
Exactly. So our question then was how we can make this turbulent patch that we generated, how can we make that vanish? That was basically the goal of our study.
So what did you end up doing?
Yeah, so we have this one turbulent puff, and the answer of how to make that vanish sounds somewhat paradoxical. So to eliminate turbulence, we basically had to create more turbulence. And what I mean by that, so we had this one puff, and we created more puffs at regular intervals. The trick then is that if these puffs get close to each other, close enough to each other, then they start affecting each other and they decay. So really more turbulence can lead to less, or in our case, really no turbulence.
So were you actually getting rid of all the turbulence, or was you just sort of changing the scale of it?
No, in our case, we were actually getting rid of all the turbulence. So the flow at the end of the pipe was completely laminar, and that's kind of the things that we are really excited about. So we didn't only reduce the level of turbulence, but completely eliminated it.
So would it work in a actual real-world pipe, which isn't as smooth as your one, or would it just work in this beautifully smooth pipe?
Okay, that's a slightly difficult question. So in our experiment, it works for pipes up to a certain flow speed. At higher flow speeds, we were up to now not able to do it in an experiment yet, but we have computer simulations which suggest that similar things might also work kind of in pipes when the velocity is higher. So it could actually work in real pipes.
So the puffs you're adding, were they exactly the same as the puff you were using to create the turbulence in the first place, or was there anything special about them?
No, the puffs are basically the same, and that basically leads to kind of a question of why can we destroy turbulence, or what is the mechanism about that? And we tried to investigate exactly that. And in order to do that, what we basically did is an experiment where we visualized the flow. We really measured the flow using a laser-based measurement technique. We looked at basically how this puff works, so where it gets its energy from. So what we basically found is that the turbulent vortices and eddies that power turbulence are created at the rear end of this puff. So they are created at the interface between laminar and turbulent flow. And so it turns out that the energy source that basically powers this turbulence requires laminar flow behind the puff. But you add a second puff, then this energy input ceases and the turbulence vanishes.
So do you have to keep on adding these puffs forever, or can you somehow get them weaker and weaker and weaker and actually kill it in the pipe entirely?
Basically, you have to add these puffs at a certain spot in the pipe locally, but then further downstream of the pipe, you don't have any puffs anymore. One can probably explain that with this probably imperfect analogy, but think of these turbulent puffs as kind of sailboats in a regatta. And at a certain point, what we do is we constantly start new sailboats that enter this race. And after some time, if these boats sail so closely behind each other, then the succeeding boat takes the wind off the sails of the boat in front of it. And that basically means that the whole entire regatta comes to a halt, and we don't find any boats downstream, or in our case, we don't find puffs downstream. So we have to add the puffs all the time, but downstream you don't have any more.
So in a real-world situation, would you sort of envisage having a pipe with a whole series of these kind of puff inducers, so it would break up the turbulence every kind of 100 metres or so or whatever, and therefore everything would flow a lot more easily?
Exactly, so that's the idea.
Would this work in any other examples, so other places where turbulence is a problem, sort of in on cars, aerodynamics and things like that?
Yeah, that's basically what we hope we can do. I mean, right now this is a proof of concept experiment. So right now we can only do that in pipe flow, and we cannot yet do it in more relevant problems like kind of the wing of an airplane or something like that. But we're super excited about our results because it shows that in principle turbulence can be completely eliminated. It's still a very difficult task, and don't expect to have cars with reduced turbulence in the next kind of 10 years or so. But we are very confident that we can get closer to this.
Brilliant. Thank you very much, Tobias, and good luck with that.
Tobias will be with us for the rest of the show, so if you've got any questions about the science of turbulence for him, or any general science questions for us, tweet at Naked Scientists and we'll pick that up, or post a comment on Facebook, or you can send us an email to chris@thenakedscientists.com.
You're listening to The Naked Scientist with Ben Valsler and Dave Ansell. Now, staying on the topic of airflow and turbulence, Mira Senthalingam and I investigated how airflow through a building can be controlled to keep it cool in summer or warm in winter.
This week on Naked Engineering, we're going to be looking into how simple principles of physics can be used when designing buildings to cool them down without the need for energy-consuming air conditioning. To investigate the design of these low-energy buildings, Dave and I have come along to the BP Institute here at the University of Cambridge. Now, Dave, to start things off, this all basically uses the principles of convection, doesn't it?
Yeah, convection is a major thing which drives fluid flows all over the universe, in fact, from the sun to the deepest ocean and in a house. So I've got a nice little experiment here to show you what's going on. I've got a little bottle filled with red fluid. It's just some hot water with a little bit of food colouring in it. When water heats up, it expands, so it becomes slightly less dense. So if we then put it in this small fish tank full of cold water and then take the lid off, the slightly less dense red warm water should float up.
Yeah, the red food colouring is moving up through the water towards the top.
That's right, and so the warm fluid will float upwards, and because its place is taken by cold water, and it's pushed up and you get a circulation.
OK, well, whilst that colouring spreads through, let's look into how this principle can be used to actually design naturally ventilated buildings. So joining us this week are Alan Short, the Professor of Architecture here at the University of Cambridge, and Andy Woods, the Professor of Fluid Mechanics. Now, Alan, how do you actually adapt this when designing buildings and therefore take into account air movement for the first low-energy building?
Well, we had a wonderful opportunity to make quite a big building in Malta, a very simple building. It was an industrial building for a brewery. We had to make one big space that would stay as cool as possible through the summer in Malta, where the temperature cheerfully gets up to 40 degrees centigrade quite often. The building didn't have very many people in it at any one moment, so we didn't need to supply them with much fresh air during the day. So our strategy was to make a very heavyweight building, very difficult to change its temperature quickly, and then as soon as the sun went over the horizon, we'd open up our chimneys and vent it as fast as we could. We achieved up to 12 full air changes an hour by about 2 o'clock in the morning. The building's starting to actually respire. You can see it breathing. And then by dawn the following morning, when the temperature inside is exactly the same as outside, you shut it up as quickly as you can, and you live off the coolness for the rest of the day.
And Andy, you look into the fluid mechanics, really, behind this flow of air. So how does it actually work, and what controls the flow of air through a building?
Well, essentially the dominant principle driving the flow is a combination of wind driving forces and buoyancy forces. And the buoyancy forces arise from the fact that air inside the building is typically warmer than the air outside the building. And so that air wants to rise relative to the air outside the building because it's less dense. So if you put an opening at the top of the building and the base of the building, the warm air will tend to rise out the upper opening, bringing in cooler air from the outside.
And to encourage this, you use stacks on your building.
Okay, so a stack is really like a large chimney on the top of a building. It provides an extra vertical distance through which you can have the warm air as it rises out through the building. And essentially this increases the pressure driving the flow between the inside and the outside of the building.
So this is actually the reason why we have chimneys anyway. So you have a big column of hot air above a fire, which floats upwards very strongly. So you get a big draft going up the chimney, which pulls all the smoke out.
That's exactly the case. And of course, with a chimney, you want the smoke to vent out of the building. But in natural ventilation, we're also trying to bring air into the building.
So to actually show this in action, though, you've got a water model here. So it's a plastic box which represents a room, but it's tipped upside down. So the floor is at the top and then the ceiling is at the bottom. But coming in through the floor, you've got a vent, and out of the ceiling there are two chimneys, essentially. And you can see a good movement of water through here. What's actually happening in this model, then?
OK, so this is a what we call a water bath model of natural ventilation. We're using salt as an analogue system to model the density changes associated with heating and cooling air. So salt water is heavier than fresh water, and so salt water sinks. And so if we turn the system upside down, as we have in the experiment, we can put a source of salt water to model a heat source. And so we've dyed that red, and you can see a turbulent plume starts rising off this little model radiator, and it rises to the ceiling in the tank, taking up a lot of the air in the room as it goes. We've also got a hole in the floor of the tank, and you can see blue fluid is coming through there, and this is the cold outside air providing fresh air into the building. This is what's called a conventional displacement ventilation system that you'd use in the summer. This is a very effective way of removing the heat from the building because, as you see, this red plume of heat goes all the way to the ceiling, and even though it does mix, it produces a layer near the ceiling of hot air which goes straight out of the space, and the occupants near the floor are actually immersed in this colder layer of outside air that you can see below that interface.
Now, this model is great then, so it clearly shows the movement of air through a building. But, Alan, how do you actually adapt this, say, for different conditions or different buildings?
There are many different recipes for different types of climate and different times of the year. You can manipulate the air before it gets into the space at the bottom. If you capture it in a plenum first, you can pre-cool it or pre-warm it naturally or help it along a bit. If you go back up to the top, you can pre-cool air as it comes in and drop it into the space, which is very effective. You can do that in a dry version, or you can mist water vapour into it, which is even more effective. And you can heat the exhaust stacks as well, just to try and induce a flow.
So this is increasing the flow because you're making the air in the stacks even hotter than it would be naturally, so driving even more convection and more flow.
And now coming back to your water model, Andy, I can see here that the hot air, or the hot water in this case, is still moving through the building and out of the stacks at the top. But what about during winter? Could this be changed to keep a building warm as well?
Winter presents a very interesting challenge because if you look at the way this system's running at the moment, the air's coming in through the low level in the building from the outside, and then the warm air is venting out through the ceiling. And so we're actually losing a lot of heat out through the ceiling to the outside. Many buildings in the UK today, the heat generated in the building from the occupants of the building who may be using computers or doing other activities in the building is typically sufficient to actually keep the building warm during the occupied times. And so what we don't want to do is actually vent away that heat through the stacks. And so in winter there's a very simple thing we can do to actually change the whole of this process. And I'll show you this by just putting this bung in, essentially closing the window at low level. And what you see now is that the inflow at the floor has stopped, and the two stacks are now doing something very different.
There's actually water flowing out of one and it's coming in through the other one now.
That's right, because we've stopped the air supply at the floor level, but we still have a space which is warmer than the outside. The warm air leaves through one of the stacks, and to replace all that air has to come in through the other stack. And this is very interesting because the air that's coming into the building now develops a cold plume that you can see falling towards the floor. And as it falls towards the floor, it mixes with the warm air in the space. So by the time it's reached the floor, it's actually much warmer than the outside temperature. And so this is a way of ventilating the building in winter when you've got a lot of heat generated in the building without needing to provide additional heat to preheat the ventilation air. And so that provides a low-energy solution to actually keeping the natural ventilation in the winter.
Now, Alan, we've discussed here then that buildings can be cooled down and also a higher temperature can be maintained, but just how much? So what are the actual temperatures we're talking about here?
Well, it's surprisingly effective. The library that we all designed in Coventry, the Lanchester Library for the university, I think the temperature there has never been recorded as being above 26.5 degrees centigrade, but we know that it's got to about 33.5 outside. So that's quite a lot of free cooling. It's 110,000 square feet, that building.
And as well as monitoring the temperature, though, it's a low-energy building. So how much of a reduction is there in the energy consumption, say, compared to using air conditioning?
Oh, well, air conditioning is a huge energy guzzler because you refrigerate the air before you heat it back up again. So a naturally ventilated office building should be using about a third of the energy of the full fruit salad air-conditioned thing.
But this is all for the design of new buildings. What about the current buildings that we have? Would it be possible to retrofit these buildings in order to give them natural ventilation as well?
Yes, it certainly is, and in fact, that's much more important than the design of new buildings, because most of the buildings that we know now will be here in 50 years' time. We're very interested in 60s and 70s buildings, which tend to be concrete framed with lightweight envelopes. You can easily start adding new things to the facade. This is a fantastically rich and interesting area of work.
OK, well, that's great. Thank you, Alan, and thank you, Andy. That's it from Dave and I this week. But look out for more of these naturally ventilated buildings in the future.
That was Mira Senthalingham, who joined me with Alan Short and Andy Woods from the Cambridge University's BP Institute. Naked Engineering was supported by an ingenious grant from the Royal Academy of Engineering.
You are listening to The Naked Scientist with me, Ben Valsler, and with Dave Ansell. And we've had a couple of questions. Dave, we've had one from Les in Over, and he said that he's seen a television programme where somebody was building a very fancy, eco-friendly house, and they have a heat pump which pumps heat out of the atmosphere into a house to keep the house warm. Now, how do they work? And importantly, Les asks, what happens when it's cold outside?
Well, a heat pump basically is a pump of heat. It doesn't really matter it does matter how big the temperature difference is, but it will pump heat from somewhere which is cold to somewhere which is warm. It's essentially what your fridge is doing. It's pumping heat from the cold inside of your fridge to the hot outside of your fridge. It does it by compressing and expanding gases. And so basically the way they're rigging these heat pumps, essentially they're taking the inside of your fridge and putting it outside. So they're taking heat from outside, then putting the hot pipes at the back of your fridge where the heat gets pumped to inside your house, so it keeps it nice and warm. The bigger the temperature difference is, though, the more electricity you need.
When you're dealing with a whole house scale, can that really work? Obviously, a fridge is quite small, it's well insulated, it's very contained. Can you really heat a house using that technique?
You certainly can, people do, and you can shift sort of between 3 and 5 times as much heat as the electricity would have produced just by running an electric heater inside.
I certainly noticed when we bought a freezer and installed it in our garage that our garage seemed to be a lot warmer than it used to be. Same sort of thing going on?
Yeah, basically it's pumping heat from inside the freezer to outside, and it's not very efficient, so quite a lot of you need a lot of extra electricity in there, so that electricity goes heating up your house.
We are joined this week by Tobias Schneider, who's a researcher at Harvard University. Tobias, I wonder if you might be able to tackle this question for us. It's come in on Twitter from David Worley94. He wants to know how or whether we could use turbulence as a renewable energy source.
That's a pretty good question, but I think that this will be hard because basically what turbulence does, it consumes energy, so it increases the dissipation of energy. Nevertheless, it's important to understand and to control turbulence in ideas of how to harvest renewable energy, simply to make, for example, wind turbines or things like that, or turbines more efficient. But turbulence in itself is not an energy source, so that shouldn't work.
OK, thank you very much. We've also had a question come through on our Facebook page while we've got hold of you, Tobias. Alan Scott wants to know if there are harmonic patterns in turbulence.
Typically there are not. Turbulence, one of the features of turbulence is that it has structure on all scales. So typically you have vortices, and a large vortex creates a smaller vortex, and so on and so forth. So you typically don't have regular patterns. However, if you are looking at theoretical work done right now, which tries to understand turbulence, then there are these regular patterns, harmonic patterns, which you observe in solutions of the underlying equations, which are computed with big computer programs, and they seem to be very important. And in pipe flow, they even have been observed in 2004. So, there are these patterns, but the patterns are extremely special. Typically, turbulence doesn't have any structure.
I guess the one place where you can use, they just sort of use some of the noise, some of these vibrations from turbulence is something like a flute, where you've got a resonator attached to something which is producing a turbulent airflow, and that turbulent airflow drives the resonator in the flute. So the air sort of rushes in and back, in and out, and that connects to the turbulence being produced as you blow over the top of the flute. And so you can get a big sort of resonance, big airflow in and out vibrations, which you hear as sound. But I guess that's the property of the resonator more than the actual turbulence itself.
Is that effect related to noisy pipe syndrome? Is it something similar going on where you turn your hot water on and you get this horrendous noise or buzzing or a low hum for a while?
I think that is, again, something very similar. You get sort of turbulence in the pipe, which produces lots of different frequencies of vibration at quite a low level. And then if you've got some air trapped inside the pipe somewhere, that can compress and expand, and it acts like a spring. So you've got a mass and a spring, so that will vibrate and resonate and build up to quite a large vibration, even if the original turbulence was lots of different frequencies to start off with and not very large.
Dave, thank you. Tobias, thank you ever so much. Dave, another question for you here, not so much about turbulence, but about fluid dynamics, perhaps. And this is from Steve in Thailand. He is wondering how the properties of cornstarch and water mix together, how the properties change so that it can flow like maple syrup when you're handling it slowly, or be really solid when you punch it, or even shatter.
Lovely stuff. I love playing with it. Yeah, cornstarch, the other side of the Atlantic, this side of the Atlantic, corn flour, is basically made up of lots of tiny, tiny particles. They really like water, so they wet very, very well. So you get lots of tiny particles surrounded by water, and that water sort of lubricates them and means they can move past one another if you apply slow forces and it flows like a liquid. If you hit it quickly, you squash the whole material very fast. The particles don't have time to move out the way, so they all kind of jam into each other and lock together until you get a solid line of particles, which locks it all up and it behaves like a solid. And so it's a solid when you hit it fast. When it flows slowly, it's behaving like a liquid. Of course, when you cook it, it's entirely different. It's no longer particles, it's polymers, and it just turns into a gloopy liquid, which is just kind of sticky and gloopy.
Thank you very much for your question, Steve. Dave, we've had this question come in on email from Ken, and he says, if wind has zero resistance, does it still make any sound? Now, the analogy he's given is with vision. He says, we can't see the wind, only see the things it moves. So he would think that we can't hear wind unless it interacts with something and that causes turbulence. What do you think?
It certainly won't cause any sound if there's nothing to cause any turbulence, if there's no vibrations, because sound is just a vibration of air. So if the wind is flowing past something and that thing makes it vibrate, like if you get some swirling when it blows across the edge of a surface or something, you get some turbulence, or that turbulence can drive vibrations in a bottle or something. When you blow across the top of a bottle, you'll produce very loud sounds. If you're in the middle of an air column, so if you're up high in the air where all the air is moving in the same direction very fast, there's no relative movements, you won't get any vibrations at all, so it would be very quiet. So people are hot air ballooning, it's very, very still, even if the wind's quite high, because they're moving with the wind. However, there's various interpretations of what he means by resistance. One of them is how gloopy it is, how viscous the fluid is.
So that's sort of the internal resistance of the fluid itself, rather than it interacting with, say, a wall. This is resistance inside the fluid.
That's right, basically how much friction there is inside the fluid itself. And fluids which are very, very viscous, things like treacle, will move very, very smoothly, and you won't get any vibrations, and it would essentially be very, very quiet. However, if there's very, very, very low viscosity, it can't lose energy by viscous flow, by friction. It can only lose it by turbulence, so the flows will be incredibly turbulent and very, very noisy.
So that goes back to what Fred was saying about how you have to put energy in to create turbulence, and then it actually loses the energy back to this internal friction.
That's right, and the more viscosity there is there, the quicker the turbulence will die away, and if there's enough, it won't form in the first place.
Thank you very much. And now we join Diana O'Carroll for our question of the week.
This week, I'm going backwards for Christmas.
Hi, I'm Terry from St. Louis, Missouri in the United States, and I'd like to know why it feels weird to move backwards.
Why is it that the forward-facing seats get filled up first on the train?
This is Don Parker. I'm a scientist at the University of Washington. I've been studying the sense of balance system and motion sickness since the early 60s. There are two basic reasons for motion sickness. One is you have conflicting motion cues from the sense of balance system in the inner ear, the vestibular system, and the eyes. The other problem is you get conflicting cues about your orientation. I've been studying which way is up for most of my life, and that's a problem. The effects of conflicting signals about how you're moving and how you're oriented are you get dizzy. Why does riding backwards make you motion sick? Well, the major reason is if you're riding facing forward, either in a bus that you can see out of, in a car if you're a child, or you're on a train riding forward. If you are facing forward, you can predict, you can prepare for turns. You can see out the window and see the bank of the curve. If you're in a car, you can see where turns are coming up. You can predict what's going to happen, and consequently, your ability to predict lets you lean into a turn. This reduces the disorientation that you feel. Why do people riding backwards get motion sick? Because they can't make those predictions that you can make when you're riding forward.
The same thing occurs when we get travel sick in the car. Your eyes, when looking at objects within the car, tell your brain you're not moving, whilst your vestibular system knows very well that you are. The two messages differ to the extent that you start to feel nauseous, and this is what Tommy A. 300 said on the forum. But why are some people more sensitive than others? Perhaps that's for another question of the week. Speaking of which, here's one from Leslie from Leicester.
I have a friend who can't see anything written in red or green on a whiteboard. Being the curious person I am, I've tried to get him to explain why this is, but unfortunately he can't remember much of his diagnosis. I've also tried to search on the internet, but can't find any similar reference, anything to do with pens on whiteboards. Only to do with general colourblind individuals not being able to see red laser points on a whiteboard. However, he swears he's not even colourblind in any other way. If one of your team could solve this mystery for me, I'd be most happy. Thank you.
What could be preventing this guy from being able to see red and green pens on a whiteboard? Normally, colourblindness only stops people from being able to differentiate between certain colours. But if you have an answer, then write to chris@thenakedscientists.com and put your thoughts on the forum, and that can be found at thenakedscientists.com/forum.
Thank you very much, Diana. That was Diana O'Carroll with our question of the week. And as always, if you have a problem that you can't solve and you think needs Diana's special treatment, then get your question to us, chris@thenakedscientists.com. But that's all we have time for this week. Next week, we're looking at advances made in preventing and treating HIV. We'll find out how researchers are studying the structure of the virus to try to develop new treatments and to prevent infection in the first place with vaccines. If you've got any questions or comments for us, you can email us at chris@thenakedscientists.com. You can post a comment on our Facebook page, or you can tweet @NakedScientists. If you'd like to catch up with anything we've done, see our experiments, or follow up on any of the news stories we've covered, join us online at thenakedscientists.com. Many thanks to our production team this week. That's Tom Simpkins, Diana O'Carroll, Mira Sentherlingham and Sarah Caster-Perry. Thanks to Tobias Schneider for joining us, and we'll be back with more great science next week.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council and UK FAST. For more information, look us up online at thenakedscientists.com.